Welcome back. We are going to continue our study of integration, moving into section 4.3, and we're going to start taking a look at the other big idea within integration, the idea of the definite integral. On the first day of this unit, I explained to you that there are two big ideas we're going to look at. The idea of the antiderivative. Here is the derivative of some function, figure out what it came from. And then the idea of the definite integral, which is area under a curve. Well, more or less area under a curve. For right now, these two things are going to have nothing to do with each other, even though they're going to use similar symbols. And in the next unit, we'll tie things together. By the way, I realize I skipped over section 4.2. To me, it just makes more sense to do 4.3 before 4.2. Things are going to be fine. Let's say I give you some function f of x with x-intercepts at a and b. The definite integral, which is an integral, f of x dx, but I'm going to put two numbers on my integral. Two numbers that I'm going to call my limits of integration. This thing over here is going to find the area between f of x and the x-axis over the interval from a to b. Actually, I don't want to call it the area exactly. I want to call it the signed area. More with this in a moment. The signed area between f of x and the x-axis over the interval from a to b. Oops, sorry. Now that should be on the screen. We don't have any idea how to evaluate these things yet. We're not going to worry so much about that for right now. But really, I just need you to understand what this symbol means. This symbol will find the area between f of x and the x-axis starting at a, going to b. Now, what I mean by signed area. If our region's above the x-axis, the signed area will be positive. If the region is above the x-axis, the signed area is positive. And in the same breath, if the region is below the x-axis, the signed area is negative. If the region is below the x-axis, our signed area is negative. Please copy that down, and then I'm going to show you some examples of setting up these integrals, and then we'll talk about how to do some evaluating. Okay, can you please take out the sheet in the packet of in-class examples that I gave you, titled Section 4.3 Intro to the Definite Integral. What we're going to try to do here is create an integral that would find the area, or signed area, but in all these cases, since they're above the x-axis, it's going to be a positive, of our region. In problem number 2, my integral is going to look like this. I'm going to find the integral of the function 4 minus 2x dx from my lowest x value, which is 0, to my highest x value, which is 2. I don't know how to actually figure this out right now, but if I did, the answer would be the signed area of that region. And I would read this as the integral from 0 to 2 of 4 minus 2x dx. Again, I call 0 and 2 my limits of integration, and 0 would be my lower limit of integration, and 2 would be my upper limit of integration. In number 4, I want to create an integral that would find this area. Well, that would be the integral of x squared dx from my lowest x value, 0, to my highest x value, 2, just like that. see if you can take a moment and set up the integrals in problems 6 and 8. Skip 10. 10 gets weird. We're not going to bother with that right now. 6 and 8, set up your integrals. In number 6, this is going to be the integral from -1 to +1 of 1 over x squared plus 1 dx. And in number 8, I think this is going to be the integral from 0 to pi over 4 of the tangent of x dx. I'd like to just go back to what we were writing in our notes for just a moment. I want to call these things my limits of integration. Those are the limits of integration. And I should probably say a tiny bit more. The a is my lower limit, and the b is my upper limit. Please do add that language into your notes. Okay, so now that we hopefully have a sense of what these symbols mean, we're going to try to do some evaluating. And specifically, because we don't really know anything right now about definite integrals, we are just going to try to do some evaluating using geometry. Evaluating definite integrals using geometry. And for our first example, we're going to integrate the constant function 2 dx from 3 to 5. Just copy this down. Okay, so the first thing I want to do is I want to see what this looks like. Well, the function 2, y equals 2, that's just a horizontal line at a height of 2. Y equals 2 is a horizontal line. I want to integrate this from x equals 3 to x equals 5, meaning I want to find this signed area. I don't have to worry about the signed part because I'm above the x-axis over here, so I'm just going to find the regular old area. I think this is a rectangle. Actually, I think this is a square. The area of this region is base of 2, height of 2. My area is going to be 2 times 2. My area is going to be 4, which means my definite integral from 3 to 5 of the function 2 dx is just going to equal 4. And this is going to be the idea behind most of what we do today. We're going to draw out our region, for the most part, and we're going to see how we can use some geometry to find the area. Granted, this method is going to be a little bit limited to only things that we know how to find the area of. We'll have to use a whole bunch of other tools to deal with things that are not as easy, but that's not going to be today. Next, let's take a look at the integral from 1 to 5 of the absolute value of x minus 3 minus 2 dx. The integral from 1 to 5 of the absolute value of x minus 3 minus 2 dx. Hopefully, you know what this graph looks like. It's a translation of an absolute value v, 3 to the right and 2 down. Please go graph that function. I'm going to keep the light off. Please go graph that function. So my vertex is at 3 comma negative 2, and then up 1 over 1, up 1 over 1, 1 back 1, up 1 back 1, up 1 back 1. I'm going to get a graph that looks something like this. I want to find the integral from 1 to 5. So I want to find this shaded region, the area of that shaded region? Well, first question for you, because these definite integrals are signed area, will my definite integral end up being positive or negative? Hopefully you said negative because we were below the x-axis. Well, we're going to find the area, and when we're done, we're going to make it negative. It's a triangle. What's the area of that triangle? Area of a triangle is 1/2 base times height. 1/2, my base is 4, my height is 2. You're going to get an area of 8/2. You're going to get an area of 4, which means my definite integral, because it's not area, it's signed area, is just going to be -4. Negative, whoops, this is not written in the right place. Negative because we're below the x-axis, 4 because that's the area of our triangle. Next one. The integral from 2 to 5 of x dx. Go graph it. Maybe I'll just draw my axes in quadrant 1 here. So just have a normal slanted line with a slope of 1, y-intercept of 0. I want to go from x equals 2 to 3, 4, 5 to x equals 5. I want to find the area of that shaded region. There are several ways you can do it. I'd like to see if you can find the area and then tell me how you found the area. So there's several ways we can do this. First of all, this shape is a trapezoid. So if you remembered the formula for area of a trapezoid, that would work. If you didn't, I think you can see this as a rectangle with a triangle above it. Find the area of each and add them together. I think you could also look at this as a big triangle. You can find the area of that big triangle, take away the area of this little triangle to get the area of the region we actually care about. I think I'm going to focus on the triangle rectangle thing. I've got a base of 3, height of 2 for that rectangle, and height of 3 for the triangle. The area of the rectangle is going to be 3 times 2, that's 6. The area of the triangle is 1/2 times 3 times 3, that's 9 halves. I'm going to add them together. 6 plus 9 halves, am I still on the screen? Oh, good, I am. I'm going to get 12 halves plus 9 halves. I'm going to get 21 halves. And we're above the x-axis, so this signed area is going to end up being positive. 21 halves is the answer to that definite integral. One more like this. The integral from 0 to 2 of the square root of 4 minus x squared dx. The integral from 0 to 2 of the square root of 4 minus x squared dx. Now, it's been a little while, but you saw this in the summer work. Graphs that look like this. If you don't remember where this came from, well, this is like y equals the square root of 4 minus x squared. If I square both sides, I get y squared equals 4 minus x squared. Or x squared plus y squared equals 4. What do you remember from last year? What is x squared plus y squared equals 4? That's a circle. This is a circle with a center at the origin and a radius of 2. Now, this, however, is not an entire circle. Because if I was solving this thing for y, and I had to undo my square, I'd have to take the plus or minus square root. Because I just took the positive square root. This is just the top half of a circle. My graph is going to be a semicircle. And it's going to look like this. Now, I want to find the definite integral from 0 to 2, which means I don't actually want the signed area of a semicircle. I want the signed area of a quarter circle. I think you could figure that out, though. What is this definite integral going to equal? Well, it's a quarter of a circle, so I want to do 1/4 times pi times r squared. My radius is 2, so I'm just going to get 1/4 times pi times 2 squared. I'm going to get 1/4 times 4 pi. I don't know why I broke it down like that. But when you're done, you're going to end up with pi. Give me one moment just to open a few more windows in here. Okay, hopefully that's a little bit easier to see. So these are basically the basic shapes we're going to have to be able to deal with. Things made up of line segments and things made up of semicircles or quarter circles. Before we look at a little bit more practice, there are a couple properties of definite integrals that we need to go through. Properties of definite integrals. First property. The integral of f of x dx of any function from a to a means find the signed area under f of x starting at a and ending at a. What do you think that's going to be? If you're starting and stopping at the same place, you didn't actually trace out anything. There wouldn't actually be any area. Your integral is just going to be 0. Number 2, if I give you the integral from a to b of f of x dx, we're allowed to switch the order of our limits of integration if we also change the sign of our answer. This is going to equal negative the integral from b to a of f of x dx. Later on, we're going to get into why we would have to do this. Right now, we're just going to focus on the calculations. But for example, if I ask you to evaluate the integral from 4 to 1 of f of x dx, well, I could switch the limits of integration. I could put the 1 on the bottom and the 4 on top of f of x dx, as long as at the same time, I also change the sign of that definite integral. This is property number 2. Property number 3. If I want to do the integral from a to b of f of x dx, let's say this is a, let's say this is b, and let's say there's some random other x value, c, in the middle. If I want to integrate from a to b, instead, I could go just from a to c, and then from c to b, and add those answers together. This is going to equal the integral from a to c of f of x dx, plus the integral from c to b of f of x dx. This whole property is really all about how I'm allowed to split a definite integral. I'll show you a bunch of examples of this in a moment. Yeah, I think that's all I want to say about that for now. 2 more properties. Number 4, if I want to do the definite integral of a constant times some function, you're allowed to take that constant and move it out front. So I'm going to say k times the integral from a to b of f of x dx. Finally, we have a sum and difference property, the integral from a to b of one function f of x plus or minus some other function g of x dx. We can kind of do what we're always allowed to do with sums and differences. We can split it into 2 different integrals. I can do the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. I'm going to pause, get 3, 4, and 5 in your notes if you haven't already. Okay, So we need to do a little bit of practice now with definite integrals using geometry and using our properties. Can you please take out the sheet that's titled Section 4.3, the definite integral? On this sheet, I'm not giving you formulas for the function. Instead, I'm just drawing out the function for you. The AP exam tends to do a lot of that, although they also will need you to recognize triangles, semicircles, quarter circles from the formula, like we just did in the notes. And we want to figure out a couple integrals here. You know what? I think you can go do A and B. Please try letter A and send your answer into Edpuzzle. Well, I want to do the integral from 0 to 2 of g of x dx. I see a triangle over here from 0 to 2. That's going to be 1/2 times the base is 2, the height is 4, so 1/2 times 2 times 4. And you're going to get 4. You try letter B. I see a semicircle over here. So it's going to be 1/2 times pi times my radius of the semicircle is 2. So 1/2 times pi times 2 squared, that's 1/2 of 4 pi, that's 2 pi. I hope, though, that you noticed that this is below the x-axis. So my definite integral isn't going to be 2 pi, it's going to be negative 2 pi. Letter C is an example of that property that says, instead of going from 0 to 7, because that's pretty involved, how about I just go from 0 to 2, and then 2 to 6, and then 6 to 7? It's kind of like I want to split this into 3 different integrals. The integral from 0 to 2 of g of x dx, plus the integral from 2 to 6 of g of x dx, plus, come on in, the integral from 6 to 7 of g of x dx. I am going to stop this. Sorry about that. Just had a visitor stop by. Okay, so let's see if we can finish this one off. In letter C, we need to find those integrals and add them together. I think we already know the first two, so really your job is just figuring out that last piece and then adding everything together. See if you can finish this. I already know that this is 4. And then I have a minus 2 pi. As for that last section, between 6 and 7, that looks like a triangle with a base of 1 and a height of 1. So that's plus 1/2 times 1 times 1. That's just 1/2. So we're going to get 4 minus 2 pi plus 1/2. Let's see, 8 halves plus 1/2, 9 halves, minus 2 pi. 9 halves minus 2 pi should be the answer in C. In letter D, thinking back to pre-calc, if you put absolute value bars around your function, what will it do to the graph? Absolute value bars around our function should make the entire graph above the x-axis. So, rather than the graph that you're looking at, we're going to have this, and then something like this, and then something like that. So really, each of the regions will end up with a positive signed area this time. This now is going to be the same thing that we did in letter C. You're going to get 4 plus 2 pi plus 1/2, and I think that should give you 9 halves plus 2 pi this time, because again, everything was flipped over the x-axis. One quick little comment that I want to make about this with absolute value bars. You are not allowed to say something like this. If we have something like absolute value of 3 minus 4 plus 2, you can't just say that's 3 plus 4 plus 2 or 9, because it's not. This is really negative 1 plus 2. This is really the absolute value of 1, which is just going to be 1. What we're actually doing is we're not trying to find a problem like this. We're really finding the absolute value of the first region the absolute value of the signed area in the second region, absolute value of the signed area in the third region. So really, what I was doing in this problem was I was doing the absolute value of 4 plus the absolute value of negative 2 pi plus the absolute value of a half to end up with the final answer that I gave you. I don't want to see this written out as the absolute value of 4 minus 2 pi plus a half, or the absolute value of what you had in C or something like that, because that would be incorrect. Next, letter E. You should have a problem with the way that was written. I'm going to go use that property that says I can make this negative the integral from 4 to 6 of g of x dx. Now, I need to go find the integral from 4 to 6 of g of x dx, and when I'm done, I'm going to change the sign. See if you can finish off letter E. Okay, well, I'm back to the original function, so I'm going to ignore this thing that I put above the x-axis over there. I'm doing the integral from 4 to 6. It's signed area, and below the x-axis it's going to be negative. I'm going to have negative 1/4 times pi times 2 squared. Negative 1/4 times pi times 2 squared. And I think that's going to give me negative pi. But there are two negatives here. The negative because you're below the x-axis, and the negative because you switch the limits of integration, which is going to make your final answer pi. Letter F. If you add 2 after a function, what will that do to the graph of g of x? It should move it up 2 spaces. Now, what I could do is I could take that graph and actually move everything up 2 spaces, but that's going to be a pain. Plus, 2 I guess was nice. If I moved it up 1, then this semicircle is partially above and partially below. It's just going to be a mess. There's a different way I can deal with this one. I can use my sum and difference property, and I can turn this into the integral from 0 to 4 of g of x dx plus the integral from 0 to 4 of the constant 2 dx. Now, to evaluate, well, this first one, you're just going to get straight from the graph. You go do that. Tell me what the integral from 0 to 4 of g of x dx is. Okay, let's see. I've got my triangle, 1/2 times 2 times 4. Then I've got a quarter circle, minus 1/4 times pi times 2 squared. I'm thinking 4 minus pi. I hope. Yep, I think that's okay. As for the other integral, this has nothing to do with the graph that you're looking at. This goes back to what we were putting in our notes. How do I integrate the constant 2 from 0 to 4? Well, 2 is a horizontal line at a height of 2. You're going to go from 0 to 4. What is the integral of 2 from 0 to 4? That's a rectangle. Base is 4. Height is 2. You should get 4 times 2. You should get 8. Your final answer to this problem is going to be 12 minus pi. Letter G. If you subtract 3 from inside a function, how does it move the graph? That minus 3 should take your graph of G and move it 3 to the right. You know what? Let me try to actually graph this thing. I had a triangle between 0 and 2. Now my triangle is going to go from 3 to 5. Oh, actually, that might be all I need. I'm going to start over there. I'm going to go down there. And then I have the rest of the graph and all that stuff. But this is what g of x minus 3 does. If you want to integrate that from 3 to 5, that means find the area of that triangle. Well, we can do that. Go do that. This is just going to be 1/2 times 2 times 4. You're just going to get 4 out of this. Because it's the same graph that we had, just moved 3 to the right. So rather than integrating the original from 0 to 2, I can integrate the one moved to the right from 3 to 5. Letter H, we can use our constant multiplier property. We can take the negative 2 up front and get negative 2 times the integral from 6 to 7 of g of x dx. You finish this one. Well, integral from 6 to 7 is a half times 1 times 1. We're going to get, I think, just negative 1 over there. There's one more thing I want to take a look at. Can you please take out the worksheet that is titled Section 4.3, Practice with Properties of Definite Integrals. I'll give you a moment to get that sheet out. I'm giving you no graph, just a little bit of information here. I'm telling you that the integral from 1 to 2 of f of x dx is negative 4. I'm telling you the integral from 1 to 5 of f of x dx is 6. Integral from 1 to 5 of g of x dx is 8. We don't have a graph, we don't have anything, we just have these 3 pieces of information. That's all we're going to need, combined with our properties, to be able to deal with some of these things. I think you can handle letter A. Go do letter A quickly right now. I don't know what g of x looks like, but I don't really care. You integrate anything from 2 to 2, you're not tracing at any area, and you're going to get a final answer of 0. To do letter B, I think we need to first use our property that says we can rewrite this. I can rewrite this as switch the limits and change the sign. I can make this negative the integral from 1 to 5 of g of x dx. I know the integral from 1 to 5 of g of x dx, that's 6. I'm going to change the sign of it. You're going to get negative 6. Negative 6. How about you try letter C? By our properties, I can take the 3 out front. I can make this 3 times the integral from 1 to 2 of f of x dx. I know the integral from 1 to 2 of f of x dx. It's negative 4. This is 3 times negative 4. I'm getting negative 12. Okay, this one's a little tricky. Letter D. I want to do the integral from 2 to 5 of f of x dx. As far as f of x is concerned, I know the integral from 1 to 2, and I know the integral from 1 to 5. How could you figure out the integral from 2 to 5? I think if I was to do the integral from 1 to 5 of f of x dx, that would be too much. That would be the entire thing. If I then take away this integral over here from 1 to 2, I'll be left with the region I actually care about from 2 to 5. So that's how I'm going to set this up. This is using that property that I said we can split it, but using it in a slightly different way. You know what? If you don't like the way that I set this one up, another way we can think about this is we can do the integral, actually, sure, why don't I show you this? I could also say the integral from 1 to 2 of f of x dx plus the integral from 2 to 5 of f of x dx is going to equal the integral from 1 to 5 of f of x dx. Well, sorry, that's a little bit of a mess. If we do it like this, I know the integral from 1 to 2 of f of x dx, that's negative 4. I don't know the integral from 2 to 5 of f of x dx, that's what I'm looking for. And I do know the integral from 1 to 5 of f of x dx. I gave that to you as 6. Negative 4 plus what would give you 6? I think that's going to be 10. If instead you see what I'm doing with this subtraction problem, you could go straight to that by doing integral from 1 to 5 of f of x dx is 6, minus integral from 1 to 2 is negative 4, and you're going to get 10 out of that. Either way will work. Sometimes I think the way on the bottom is a little bit easier. Letter E. I'm going to go use my sum and difference property It says I can rewrite this as the integral from 1 to 5 of f of x dx minus the integral from 1 to 5 of g of x dx. Finish it off and tell me the answer. Pulling this information from what was given, this looks like 6 minus 8. I'm getting negative 2 out of that. You go do letter F. Using my sum and difference property along with the constant property, I can write it like this. 4 times the integral from 1 to 5 of f of x dx plus the integral from 1 to 5 of g of x dx. This is 4 times 6 plus 8. 24 plus 8, you're going to get 32 out of that. Let's see if you can do a few more of these. Number 2, letter A. See what you can do in 2A. Well, let's see. I think to go from 2 to 7, I can do the integral from 2 to 5 of g of x dx plus the integral from 5 to 7 of g of x dx. I think that's going to give me 5 plus negative 3. I'm going to get 2 out of that. Try letter B. Three times the integral from 2 to 7 of f of x dx minus 2 times the integral from 2 to 7 of g of x dx. Let's see here. Okay, 3 times the integral of f of x dx from 2 to 7, that's 3 times negative 8. Minus 2 times, well, I know this integral from what I already calculated in letter A, I'm going to get a 2 there. This will give me negative 24 minus 4. I'm getting negative 28 for that one. Try letter C. I don't like the limits of integration. I'm going to change them. Negative the integral from 2 to 5 of g of x dx. That's just negative 5. Okay, next one. Letter D. This is that trick that we've seen before of we need to split this into 2 integrals. The integral from 2 to 7 of f of x dx plus the integral from 2 to 7 of 5 dx. You'll get this from the original problem. You'll get this from using some other geometry ideas. See if you can go from there and get the answer. Okay, from 2 to 7 of f of x dx, that's negative 8. Plus, what is this thing? That's a horizontal line, 1, 2, 3, 4, 5, at a height of 5, going from 2 over to 7. That's a square. Base is 5, height is 5. 5 times 5, we're getting 25 out of this. Negative 8 plus 25, your final answer will be 17. Exact same idea in letter E. Try letter E. This is the integral from 5 to 7 of g of x dx minus the integral from 5 to 7 of 3 dx. I'm going to get this information from over here. That's negative 3 minus. Okay, well, this is a horizontal line at a height of 3. I'm going from 5 over to 7. 2 times 3, that's 6. Negative 3 minus 6, that is negative 9. Letter F. Integrating g of x plus 3 dx from negative 1 to 2. Well, the x plus 3 would move our graph of g. How? Should move it to the left 3 spaces. I have no clue what g looks like. I'm just going to kind of do some random sketching here. Let's see. I know that between 2 and 5, I have some function g whose signed area is a positive 5. And then from 5 to 7, the signed area is a negative 3. I have no clue what this actually looks like. I'm just making something up. If I then move this thing to the left 3 spaces, well, it's then going to look something like this, which means that the integral from negative 1 to 2 of the version of g that was moved to the left 3 spaces is the same as the integral from 2 to 5 of the original, before I moved it to the left, g of x function dx. I know that this thing had a signed area of 5, so this thing over here is also going to have a signed area of 5. A few more for you to try on your own, on the back. I don't think there's really anything new here. Try letter A. Okay, well, let's see. I know that if I go from negative 3 to negative 1 of f of x dx, and I add to that the integral from negative 1 to 2 of f of x dx, I'd get the integral from negative 3 to 2 of f of x dx. This is what I'm looking for. This, I kind of gave it to you. You know what, I don't really like this problem over here. How about I change this to the integral from negative 1 to 2 of f of x dx? That's going to equal negative 4. Now I can say this is the thing I'm looking for. Plus negative 4 equals this thing over here I told you was 6. What's the integral I wanted to find? It's 10. Try, let's see, yeah, try letter B. This is going to equal negative the integral from negative 3 to 2 of f of x dx. That's negative 6. Try C. Negative 1 to 2 of 5 times the integral from negative 1 to 2 of f of x dx minus the integral from negative 1 to 2 of 4 dx. Okay, I already know that that first integral is negative 4, so 5 times negative 4 minus, as for the other one, constant function of 4, 1, 2, 3, 4, from negative 1 to 2. That's 3 times 4. So I'm going to get negative 20 minus 12. I'm going to get negative 32 for that one. Last one, try letter D. Okay, constant function of 6, 1, 2, 3, 4, 5, 6, at a height of 6, starting at negative 3, going to 2. Looks like my base is 5, my height is 6, so 5 times 6 minus 3 times. Well, that next one, I gave you what that next one was. I told you that was 6. So this should be 30 minus 18, should give you a final answer of 12. And this is how we can find definite integrals if the graph is either made up of line segments and parts of circles, or we're just given a little bit of information. If we have some other graph, though, like a parabola, and want to find the area under a parabola, we need a few more tools before we can get there. And that's what we're then going to look at over the next 2 weeks in section 4.2, how to find the areas when we can't just use geometry and things aren't just given, like in these properties.